Hello, friends. Welcome to Decluttered. Wishing all of you a Happy New Year. Over the past few weeks, I have been conducting some sample paper solving for CBSE Class 10th in Maths. And one of the feedback that I have been getting consistently from the people solving the paper is that they find trigonometric ratios and identities challenging. When I was in your place, I had similar concerns. Through this video, I want to share with you what worked well for me and how I believe you can address some of the challenges that you might be facing in trigonometric ratios and identities. Let's begin. In this episode, I will cover the basic trigonometric ratios, the trigonometric identities, approaches for the questions, and some sample questions. So let's come to the basic trigonometric ratios. As we all know, there are 6 trigonometric ratios. If I call this the perpendicular, base, and this the hypotenuse. It's a right angle triangle, ABC, right angled at D. We know by Pythagoras theorem, h square is equal to b square plus b square, where h is the hypotenuse, b is the perpendicular, and d is the base. We also know that for this angle theta, sine theta is equal to b by h. Cos theta is equal to b by h. Tan theta is equal to b by b. Cosec theta is equal to h by b. Sec theta is equal to h by b. Cot theta is equal to b by b. These are the 6 trigonometric ratios. What I do is, I call these 2 trigonometric ratios as the basic trigonometric ratios. All the other trigonometric ratios can be expressed in the form of sine theta and cos theta. We know tan theta is equal to b by b, which is equal to b by h by b by h, which is equal to sine theta by cos theta. Similarly, cot theta is equal to b by b, which is equal to b by h by b by h, which is equal to cos theta by sine theta. This is also equal to 1 by tan theta. Cosec theta is equal to 1 by sine theta, and sec theta is equal to 1 by cos. These become the derived trigonometric identities. Now, this is the nomenclature that I use, right? So, I will just come to the next page. Tan theta is equal to sine theta by cos theta. Cos theta is equal to cos theta by sine theta, which is equal to 1. So far, so good? Perfect. Now, let us look at this triangle theta, B, B, and Z. This is 90 degrees. We know alpha plus theta plus 90 degrees is equal to 180 degrees. So, alpha plus theta is equal to 90 degrees. That will give me alpha is equal to 90 minus theta. Right? Let's go to the next page. Now, sine alpha is the perpendicular opposite alpha, which becomes b, which becomes b by h, which is equal to cos theta. Cos alpha is equal to the base around alpha, which is p now, p by h, which is equal to sine theta. Tan alpha is perpendicular to alpha, which is p, and the base, which is, sorry, perpendicular to alpha, which is b by p, which is cot theta. But we also know alpha is equal to 90 minus theta. So we end up with sine of 90 minus theta is cos theta. Cos of 90 minus theta is sine theta. And tan of 90 minus theta is cos theta. Same way, cot of 90 minus theta. So far, so good. So far, so good with complementary angles. I will give a short pause of 1 second here for you to go through the work. You can also pause the video to go through. Fair. Also remember that sine theta and cos theta in my lingo are basic trigonometric ratios. Everything else are derived trigonometric ratios. Now let's move on to identities. All right. Now let us come to trigonometric identities. These identities are nothing but just a different way of expressing the same Pythagoras theorem that we've been studying for ages in terms of trigonometric ratios. If in the exam you ever get confused around whether to use cosecant and cot or secant and cot or secant and tan with a plus sign or a minus sign, just come back to the basic Pythagoras theorem and derive it. It will not take you more than 2 seconds. I'm just going to draw a small right angle triangle at the top for our reference. Perpendicular, base, height, theta. All right. Now we know p square plus b square is equal to h square. This is our Pythagoras theorem. Any confusion? No. Divide by x square. Divide by square. Divide. There are three terms, p, b, and h. I will divide both sides by h square in column 1, p square in column 2, and b square in column 3. So if I divide by h square on column 1, I will get p by h the whole square plus b by h the whole square is equal to 1. And from the figure in red, we know p by h is sine square theta plus cos square theta is equal to 1. Now, if I divide by p square as per column 2, I will get 1 plus b by p the whole square is equal to h by p the whole square. H by p is nothing but the inverse of sine, which is cosecant. And b by p is nothing but cot. So we have 1 plus cot squared theta is equal to cosecant squared theta. Same way, when I divide by b square, I have b by b the whole square plus 1 is equal to h by b the whole square. And again, p by b is tan theta, h by b is inverse of cos, which is secant theta. Tan squared theta plus 1 is equal to secant squared theta. These are the three trigonometric identities that have hounded most of the students in class 10. One easy way that I use to remember the relation between cosecant cot or cosecant tan is that this is a C and this is a C. So cosecant has a relation with cot. Alternatively, secant has a relation with tan. And sine and cos are basic trigonometric ratios. So that's a relation in itself. Perfect. Now, let us move on to some ways or approaches in solving basic trigonometric ratios and identities questions. Most of the questions that come from this chapter are usually to prove LHS is equal to RHS. The first step that I do when I'm trying to solve a question is look at the LHS, look at the RHS. If the RHS is in basic trigonometric ratios, and by basic, I mean sine and cos, then convert LHS to basic trigonometric ratios if the LHS is in terms of a secant or a tan or a cot, so on and so forth. If the RHS is not in the basic trigonometric ratios, do not convert LHS yet. Maybe along the way or along the answer we might have to, but that may not be your first step. The second thing that helps me are the three trigonometric ratios. Sine square plus cos square is equal to 1. This can also be written as sine square is equal to 1 minus cos square. This can also be written as cos square is equal to 1 minus sine square. Same way, if I look at 1 plus cot square is equal to cosecant square, I can write this as cosecant square minus cot square is equal to 1, or cosecant square minus 1 is equal to cot square. Secant square minus 1 is equal to tan square, or secant square minus tan square is equal to 1. Why are these important? For a very important algebraic identity that we've learned in our 8th grade. A square minus b square is equal to a minus b into a plus b. A lot of questions just use this algebraic identity to simplify forms of cos square is equal to 1 minus sine square, where you can write cos square is equal to 1 minus sine into 1 plus sine, or cosecant square minus cot square is equal to 1. So you can write it as cosecant minus cot into cosecant plus cot is equal to 1. Let me just write it with an example of cosecant for you. Cosecant square minus cot square is equal to 1. So that will be cosecant minus cot into cosecant plus cot is equal to 1. Right? So these basic ratios, if the RHS is in the basic trigonometric ratio, convert your LHS also to the basic trigonometric ratios as first. Otherwise, the three trigonometric ratios that we used, along with a combination of this algebraic identity, forms the crux of most the questions. The fourth thing that forms a crux of some of the problem solving, in my terms, what I use, although it's not rationalizing, but we have learned a similar concept in rationalizing of denominators, and I'm going to use that. Rationalization. While trigonometric ratios, and what I mean by rationalization, as an example, is this. If I have as 1 minus sine theta. This I can write it as 1 plus sine theta by 1 plus sine theta into 1 by 1 minus sine theta, which will give me 1 plus sine theta by a plus b, a minus b, a minus b the whole square, which is equal to 1 plus sine theta by cos square theta. Now, this is not rationalization, because if sine theta is a rational number, the denominator is rational, and I'm not necessarily rationalizing the denominator. But this is a concept we learn for rationalization of denominators, and I'm just using that word to indicate the method I'm doing. Don't go by the word rationalization and simply say that this is not rationalization of the denominator. This is a very, very strong method when it comes to solving some of the questions in trigonometry. All right, now we'll look at some questions and see how these methods are helpful for us to solve some tricky questions. I will show you 3 to 4 tricky questions, and then I will request you to go back to your textbook or any practice places to practice for more such questions. The first question that I would like us to look at and do is secant A plus tan A minus 1 into secant A minus tan A plus 1 is equal to tan. Take a moment to think what the approach is. The brute force approach, like anyone would do, is open the bracket by multiplying each term with the other term. Secant A into secant A, secant A into tan A, secant A into 1, tan A into secant A, tan A into tan A, tan A into 1, 1 into secant A, 1 into tan A, 1 into 1. But that's a grunt way of doing the problem. It's not a smart way of doing the problem. LHS can be written like this, where tan A minus 1 becomes my second term, secant A becomes my first term. By taking the minus common from tan A plus 1, I can write it as minus of tan A minus 1. So this is A plus B, A minus B, which is secant A the whole square minus tan A minus 1 the whole square, which is equal to secant square A plus minus tan square A plus 1 minus 2 tan A. And tan square A plus 1, this is equal to secant square A. So that will give me secant square A minus secant square A cancel, minus into minus 2 tan. Hence proved. All right. Now let's look at another question. 1 plus sine theta minus cos theta by 1 plus sine theta plus cos theta. The whole square is equal to 1 minus cos theta plus cos. Look at the LHS and the RHS. LHS has a square, RHS does not have a square. Also, 1 minus cos theta, 1 plus cos theta. Now, this entire concept of sine theta is the thorn between us and our marks, along with the square. Give it a couple of minutes, think what could be the solution, and then continue with the video. All right. So what I will do is I will write this as 1 minus cos theta plus sine theta by 1 plus cos theta plus sine. This can be written as 1 minus cos theta, where 1 minus cos theta becomes A and sine theta becomes B, plus sine squared theta plus 2 sine theta into 1 minus cos theta by 1 plus cos theta whole square plus sine squared theta plus 2 sine theta into 1 plus cos theta. Again, 1 plus cos theta is A, sine theta is B. Let me just write the numerator and denominator separately on the next page for us. So the numerator is 1 minus cos theta, the whole square, plus sine squared theta, plus 2 sine theta into 1 minus cos theta. Sine squared theta from the first trigonometric identity is nothing but 1 minus cos squared theta. And 1 minus cos squared theta is nothing but 1 minus cos theta into 1 plus cos theta, coming from the algebraic identity a square minus b square is a minus b into a plus 1. So I can very well write the numerator as 1 minus cos theta the whole square plus 1 minus cos theta into 1 plus cos theta plus 2 sine theta to 1 minus cos theta. Now we have 1 minus cos theta, 1 minus cos theta, 1 minus cos theta common. So I will take 1 minus cos theta out of the brackets, and the remaining term is 1 minus cos theta plus 1 plus cos theta plus 2 sine theta. This and this cancel. I will get it as 1 minus cos theta into 2 plus 2 sine theta. If I do the same thing with the denominator, I will get the denominator as 1 plus cos theta into 2 plus 2 sine theta. And since 2 plus 2 sine theta is common in both the numerator and denominator, they will get cancelled. And we are left with the LHS being 1 minus cos theta by 1 plus cos theta, which is nothing but this is equal to the RHS. Perfect. So I have shown you two problems which use the basic trigonometric identities and also how rationalization of the denominator helps in. Now let me show a question wherein rationalization of the denominator is a useful concept. Let's look at this question. 1 by 1 plus sine A plus 1 by 1 minus sine A is 2 secant square. 1 by 1 plus sine A plus 1 by 1 minus sine A is equal to 2 secant square A. The first approach is take the LCM of the first term and the second term, add them, and complete. The second approach, I will just write this as 1 by 1 plus sine A into 1 minus sine A by 1 minus sine A plus 1 by 1 minus sine A into 1 plus sine A by 1 plus sine A, which will give me 1 minus sine A by 1 minus sine square A plus 1 plus sine A by 1 minus sine square A. This and this cancel, and therefore 2 by 1 minus sine square A. 1 minus sine square A is nothing but cos square A, and 1 by cos square A is nothing but secant square A. This is equal to 2 secant square. Perfect. So these are some questions. How trigonometric ratios. One question, last question that I will show you on how conversion of derived trigonometric ratios into basic trigonometric ratios should be the first step. Let's look at a question. Secant A minus tan A, the whole square is 1 minus sine A, 1 plus sine A. As I had said that if my LHS is in basic trigonometric ratios, first step is to convert RHS into basic trigonometric ratios. And that's what I am going to do here. I'm going to write this as 1 by cos A minus sine A by cos A. The whole square is my LHS. Problem solved. This can be written as 1 minus sine A, the whole square by cos square A. From the first trigonometric identity, we know cos square A is equal to 1 minus sine square A, and 1 minus sine square A is 1 plus sine A into 1 minus sine A. And 1 will get cancelled with this. I will be left with 1 minus sine A by 1 plus sine A. Perfect, friends. So this is how some basic tips will probably make your life easier when it comes to trigonometric ratios and identities. If you like this video, like, share, and subscribe. Also, leave any feedback or comments below in the comment section. Share it with your friends and family so that they are also able to get the benefit of the video if you found them. All right. Thank you. Until next time.